other idea is how do we deal with trigonometric integrals, and in particular, the goal is to solve this type of integrals. So to evaluate integrals of the form sine some power times cosine some power, so product of sine and cosine, and also product of secants and tangents. So secant to some power times tangent to some power.
You're right, I have not done this. You're very right.
Okay, so that's the goal. Now, of course, you could say cosecant product of cosecants and cotangent, but the point is that whatever technique we discuss for product of secant and tangent, the same technique will apply for cosecant and cotangent because the relationships are very similar to each other. Okay, so just keep that in mind. All right, so first we're gonna focus on products of sine and cosine. Those are the easy ones, the easier ones, and then we're going to spend some time on secant and tangent. There are more cases that we have to analyze. What do I mean by cases? Because it all depends on these powers m and n, whether they're even, odd, or sometimes one of them is 0, or both of them are different than 0, and all those combinations we need to analyze. We could do it in general, but then it may look a little bit cumbersome. So what I'm gonna do is I'm gonna show you the variation that we're gonna do concrete examples, and the idea is hopefully you will realize that whatever technique we use for the concrete example, then you can extend that to any other example that you get in that case. Okay. So if I explain you how to do, for example, sine to the 4 times cosine to the 7, and what that matters is that the power of sine is even, the same technique that we do there, you can apply it for sine to the 10 times cosine to the 7, or whatever, as long as you have an even power for sine. Okay. So I'm gonna do concrete examples so you can really hopefully understand what we're gonna do. Anyways, first one, let's focus with products of sine and cosine. So products of sine and cosine. So these are integral, the one that we have in mind now. Sine to some power times cosine to some power. Because these are trigonometric integrals, of course, some identities will be needed. So let me write down the identities that we're gonna need for this. So the first one, of course, is the Pythagorean identity, the fact that sine squared plus cosine squared, what is this? 1. This is 1. Now, typically we're not gonna use it like this, okay? So typically we use this in the following form. This means that sine squared is the same as 1 minus cosine squared, or cosine squared is the same as 1 minus sine squared. So think of this as having a way of turning sines into cosine or cosines into sine. All you need is an even power. Okay? Every time that you have sine to an even, this tells me that every time that I have sine to an even power, I can turn that into a bunch of cosines. That's what this tells me. And similarly here, if you have cosine to an even power, I can convert that into a bunch of sines. Okay? So we want to, yes?
If, let's say it was sine to the 4th.
Yes.
You just do sine to the 4th equals 1 minus cosine to the 4th?
No.
Okay, so
you have to do sine square. Okay. Just 4 is 2 times 2. Sine square, then the sine square you turn into 1 minus cosine square, and then you expand the square. That's why I said a bunch of cosines. Okay. We're going to see in the example. In the example you will see. But the idea is that when the power is even, you can go from sine to cosine or the other way around. Okay? But yeah, don't make up the stuff identity. Is sine to the 4 is now 1 minus cosine to the 4. We only have this for sine squared. Yeah. Okay, so that, of course, this is also useful to know. Derivatives, right? So what's the derivative of sine? Cosine. We're going to need this. And also derivative of cosine? Negative sine. So to keep this in mind. And then for a particular case that we're going to analyze, we also need to remember the double angle, the reduction formulas. Reduction formulas. The sine square, you remember this from trigonometry? This is 1 minus cosine of 2x over 2. We call this a reduction formula because it takes a power 2 and then you write it as a linear power. You get rid of the power. Okay? And also we have the cosine version. cosine squared, that's 1 plus cosine of 2x over 2. So the formula is the same for both, it's just that for sine you subtract and for cosine you add, okay? We're gonna need this. These are called reduction formulas. And they follow from the double angle formula. Okay? All right. So let me show you and outline to you. Here is my 1147 class from a couple of semesters ago. Let's see, when did we do this? Should be lecture maybe 26. Here, reduction formulas. And there they are. Maybe in 1147 it makes no sense to you, but you need them. You do that in, this is the trigonometry part. You do that in trigonometry because you need them for the stuff that we're going to do now. Okay? You need those for calculus too. So those are the formulas that I'm talking about. And for example, let me take advantage of this. And this is a typical exercise that you used to do back in 1147 or trigonometry, but then it probably made no sense to you. Now you will see why. Here's what you were asking. If you have sine to the 4, then we will write a sine squared squared. Now here I don't want to do the 1 minus cosine squared. Here what I'm trying to do is reduce the power. So the purpose of this problem is to write sine to the 4 without powers. So what you do is you write a square squared, then you reduce the power using the reduction formula for sine squared, expand this, and then we reduce the power one more of the cosine squared. You can write it this one. So you can imagine now, since you already know integrals, if you want to integrate sine to the 4, what do? Play this game, and then you integrate this right-hand side instead. It's easy to integrate. You know how to integrate this, right? There's a constant, there's a cosine, and there's a cosine. Very easy to integrate. Okay? So that's why we need these identities. That's why you learn this back in trigonometry. And you know, same game for cosine to the 4, for example. That probably had no meaning for the students at that point, but I told them, you will need this in Cal 2. Half the class, or most of the class, were rolling their eyes like, I'll never take Cal 2. You know. So, but.
And then there were the few that didn't know they were going to take Cal.
So we get there. Okay, so that's why, that's for the type of interest that we're going to need this identity. Okay, so when you have sine to an even power and no cosine whatsoever, or when you have cosine to an even power, no sine whatsoever. That's when we're going to take advantage of this technique. That's sine to the 4, cosine to the 4, sine to the 6, etc. Okay, so these are the identities. So for this section, you have to make sure you review this. Hopefully this is, maybe this is slightly new to you. If you don't remember, these are, I guess, the ones that you may need to memorize at this point. But I expect that you already know the previous ones that I wrote, right? You know those. So let's see how we use them. All right. So first, there is always an easy case. Most of the time, there are many integrals that reduce to the easy case. So let's talk about the easy case first. So what's the easy case? Okay, somebody's actively writing. Wait. Been too long. Yeah, so if you need a trick refresher, remember we have in OpenStax you have a trigonometry book that you can look at. Okay, so you can look at what you need in there. All right, so the easy case. So what's the easy case? The easy case is when either m or n are equal to 1. It doesn't really matter. Okay, in other words, if you have let's say the m equals 1 case, we say that m was the power of sine. So that is if you have sine, just one sine, and then cosine to whatever you want. Doesn't matter. And the other case would be when you have sine to whatever power you want, but then there is only one cosine. If you manage to do this, this is super easy. Let's see. How do we do the first one? Very good. Just a little u sub, right? So here we let u equals cosine, because then what's the u? That would be negative sine, and then we're good to go. So this becomes the integral of u to the n u to the n times negative du, right? Sine of x dx negative du. So this would be minus u to the n plus 1 over n plus 1. So you get minus cosine to the n plus 1 of x over n plus 1. So moral of the story, if you have only one sign and then cosine to whatever power, you can always make this little use of. And hopefully you see that the other case is similar, right? The same idea is just that. What should be our use of here? So we let u equals sine. And so du is just cosine. So this becomes the integral of u to the m du. So that's u to the n plus 1 over n plus 1. So we get sine to the n plus 1 over n plus 1. Okay? So that's the easy case, and whenever you can reduce an integral to a case like this, then we're pretty much done, right? Because then we know what to do. All right, so now what are the interesting cases? So those are the easy cases. Now the other cases. So for example, what if one of the powers is odd? So m or n are odd. So one of them, doesn't have to be both of them, just one of them is odd. I'm going to tell you what to do, then I just need to tell you what to do when both of them are even. Okay, and that will cover all the cases for this.
Both of them are odd.
Eh?
Both of them are odd.
At least one of them. If both of them are odd, then one of them is odd, right? What does it say here? Or. Right? So if both of them are odd, that's okay. One of them is odd, right? As long as one of them is odd, what we're about to do works. Okay, so like I said, I'm going to illustrate this with example, but the technique can be extrapolated pretty easily. Let's see. Let me do interesting one. How about this one? Because to save time, I wanted to do 2 examples for each, but I think I should do one. And then if anything, next time we revisit the whole techniques again. But if I want to have time to do everything, I cannot do a bunch of examples in each little case. Otherwise.
Are you trying to get through the whole lesson?
Eh?
Are you trying to get through all 3.2?
I will try to, if I can. At least to present the techniques to you so you can start working, doing homework and all of that, right? Okay. But again, what we do here is exactly the same thing for the other integrals, okay? For example, here we have a product of sine and cosine, and it turns out that the power of sine is the one that is odd, okay? So what is the technique here? What is the idea? All right, so why do I want an odd power? Because when you have an odd power, what can I do? I can separate a sign, and then the remaining power will be even, if you do minus 1, right? That even power, what can you do? You turn it into cosines. Now you have a bunch of cosines and one sign that you separated. So what do? You let u equals cosine, and then you have the du, and you get a polynomial, and you solve the integral of the polynomial. If you understand the technique, that's the idea. So you look at the guy that has the odd power, take out one, then you have an even power, turn it into the other one, and make it you solve. That's it. Okay? So we're gonna see it now in the sample, but that's the idea. So this guy is odd. So what I'm gonna do is I'm gonna split this as sine to the 4 times sine. So this right here will be my du. This right here will be my du, so I'm not gonna touch it. Now my job is to turn everything else into cosines, so we can make our use of. And like I said, whenever you have an even power, you can always turn into a cosine. You can exchange between the two. So now that's what I'm about to do, okay? So I'm gonna rewrite this as sine square, because that's 2 times 2, right? If this would have been a 6, then you write a sine square cube, okay? I mean, in serious, if this was a 20, you will need to write a sine square to the 10. So then you will need to do something, a binomial to the 10, okay? I'm not saying this is gonna be nice when the powers are high. This is tedious, but at least we know how to do it, okay? And now this sine square, I will write it as 1 minus cosine square. So this becomes cosine to the 4 times 1 minus cosine square times sine of x. Did you understand this?
Yes.
Now we have everything is cosine except this last guy. So I'm gonna make my substitution.
Wait. What happened to the 2?
What 2?
Isn't it 1 minus cosine 2x over 2?
No, sine square. I use the fact that it's 1 minus cosine square. The very first identity, Pythagorean identity.
Oh, you didn't do the other one.
No,
Gotcha.
Pythagorean. Remember. So these identities here are the ones that allow you to go from one to the other, from sine to cosine or from cosine to sine. Okay, that's a way to think about that. How you can change one into the other. It's just that you need even powers. All right, so if you have an odd power, that's why we take one, that will be our du, and then the other stuff we turn into the other function. Okay, so now we let u be equals cosine, and therefore du is negative sine, and then we're good to go. So this now becomes the integral of u to the 4 times 1 minus u squared times negative du. And as promised, what we have here now is a polynomial, and we know easily how to integrate polynomials, right? So let's just finish this. I'm gonna put the minus outside. So that will be u to the 4, then 1 minus 2 u squared plus u to the 4 du, distribute. So that's u to the 4 minus 2 u to the 6 plus u to the 8 du. Okay, and then this is going to be, again, I'm going to distribute the negative also. So minus u to the 5 over 5 plus 2 u to the 7 over 7 minus u to the 9 over 9, and then put back your cosine. This is all right. Questions? Did you understand this one? So whenever I'm notice that it's really irrelevant whether the odd was for the sine or for the cosine, right? You can play the same game. If the 5 would have been the cosine instead of the sine, do the same thing. Separate the cosine, turn the remaining even cosine into sine, and make your use of. Yes? So this technique works every time that you have a product and one of the powers is odd. Okay? Even if the other one is not around. So let's see. Why don't you try this one? Let's see, cosine, do cosine cube. Do this integral. Give you 1 minute. This is a cube.
With just a cosine in there, no sine with it.
No sine. So I want to tell you that it doesn't matter if there is nothing. As long as the power is odd, that's all you need. Because think about it. What role did the cosine to the 4 play here in this problem that we just did? What role did cosine to the 4 play here?
We distributed it into the 1 minus cosine squared.
But was that essential to solve the integral? It actually just made the powers larger, right? This polynomial. If we didn't have the cosine to the 4, you know, everything would have been nice. This wouldn't be here. This u to the 4 wouldn't be here, and then we just integrate this degree 4 polynomial instead, right? So in other words, this cosine to the 4, all it did was it gave me higher powers here, but it didn't really change the complexity of the integral. Okay, so whether it is there or not doesn't matter, and that's what I want you to understand. So if you see this, so now the sine is missing, just use the same technique. separate cosine, the other stuff turn it into sine, and then make your use of and you have your integral. If you had a sine in there, you will need to distribute it after you do the use of, but there's no need to distribute it. All right, so what do we get?
I got sine of x minus 1 over 3 sine cubed plus c.
Okay, hold on. So let's split. So what do we get when we split?
I split the cosine of 2x and cosine, and then I turned it into sine.
So cosine squared times cosine. Then
1 minus sine squared times cosine of the x.
1 minus sine squared times cosine. Okay, are we ready to make use of?
Yeah.
All right, what is our u?
Sine of x.
Then we let u equal sine. What's the u?
Cosine of x.
Cosine dx. And notice that's right there, all we need. So this becomes 1 minus u squared du, right? So remember, if we had some sine to a power, that would just be multiplying this parenthesis. That would be a u to whatever multiplying here, right? So it doesn't really matter whether it's there or not. So this would be u minus u cubed over 3 plus c, and now we put a sine back, right? So sine minus 1 over 3 sine cubed. Do you understand the idea? All right, so that's what we do when one of the power is odd. Okay, what if both are even? What do we do if both of them are even? Okay, that's the other case that we need to analyze. So if one of them is odd, we understand what's going on. Now, case number 2, what if both powers are even? So both mn are even. Okay, so there are 2 cases here to understand. Because remember, even could mean that one of them is 0. Okay, in other words, none of them is so that let's say m is 0. So sine is not there, but the cosine is to an even power, not an odd power like we had before. Okay, it's an even power. So let's see what happens. What do we do when one of them is 0, and then what do we do when both of them are different than 0? Because if both are 0, then there's no integral to calculate, right? It's just the integral of 1. So first, and the idea is that once you understand what to do when one of them is 0, the other case reduces to this previous case of one of them being 0. So if we understand one of them 0, then we know the other case as well. So 2.1, m equals 0 or n equals 0. Okay, one of them. So let's see, I'm going to illustrate this via example. So let's first do sine squared. So this would be the case when n is 0, right? Because remember, n is the power of the cosine, okay? So we do this one, and then we do cosine to the 4th. This would be the case when m is 0, right? But the point is that it's the same thing. All right, so as you saw earlier, what's the idea here? What we're going to do is we're going to use the reduction formula, okay? So we use the reduction formula to turn the sine square into something linear. So using the identity, sine squared turns into 1 minus cosine of 2x over 2. So the trick here is use reduction formula. The last formulas that I wrote above, you use that one. Okay?
This is only when it's 0.
Yeah, when you
This
have
is like generally
when you have sine to an even power.
So not like it doesn't matter. Like if both of them are not 0,
It doesn't only,
then it's
not
still
this case.
using the reduction formula.
We're not there yet.
Okay, I want to discuss.
We're not there yet. First understand this.
Okay.
We are in the case, we already understand what happens when one power is odd, right? Now we are analyzing what if both of them are even, and we're in the particular case in which actually one of them is not there, it's 0. So you only have sine to an even power or cosine to an even power, okay? Let me explain what to do when we have 2, and then we see what to do when the power is higher, and then one using the cosine, just so we have something different. But of course, whatever we do for cosine to the 4th is the same thing that you will do for sine to the 4th, or to the 6th, or whatever, okay? All right, if the power is 2, it's easy. Just use the identity, and now we know exactly how to do this integral, right? So what's the integral of 1? It's just x minus, what's the integral of cosine of 2x? That's sine of 2x over 2, right? Plus c. So we get 1/2 x minus 1/4 of sine of 2x. And if it would have been cosine squared instead, it's the same thing. Use the same formula, just that this would be a plus instead of a minus. Okay? So we'll have a plus here instead of a minus. But the outcome will be the same. Now, what if you have still an even power but higher than 2? Okay? And the next case would be 4. But whatever I do here, the same idea applies to power 6, power 8, etc. It's just that the higher the power, the more tedious this is going to become, as you're about to see. Okay? But tedious doesn't mean hard. Tedious means tedious. But you can do it. Like if you have to sit here and do x plus 7 to a 20, this is not hard. It's just super tedious. Right? You have to sit there and multiply, but that's life sometimes. It doesn't mean that you're going to have to do it on the exam. But you know, if this, something like this, I don't consider it to be hard. To do something like this, doesn't mean that if you need to expand this is not hard. It's just tedious. Okay. So when something like this, I will call it easy. So when you hear me saying, "Oh, now it's easy," what I mean is we can do it. Okay. Whether it's tedious or not is a different story. Okay. So that's what happens in these sort of cases. Because what's the idea? Okay, you have an even power. So what we're gonna do is we're gonna reduce the power. Okay. If you want, you can do it as an exercise outside of the integral, like the trig exercise that I showed you earlier, okay? And then you put your answer here and you integrate, or you can do it here in the same integral. It's up to you. I think it's cleaner if you go outside of the integral for a second and do the trig exercise. In other words, you go outside and then you reduce the power, and then when you get it, you put it inside your integral, okay? That way the problem looks cleaner. You don't forget to write the integral sign and all that. So I want to write cosine to the 4 without powers. So the technique is that we write it as cosine square. Why? Because I know how to take a square and write it as a linear. So we're going to write the parentheses as a linear expression. Then we distribute the square. And whatever square survives, we write it as a linear expression again, using the formula one more time. Okay? If this would have been a 6, then you have a cube here. So when you write this as a linear, you will need to cube the parentheses and deal with what you have left. Okay? And if you have an 8, then it will be a 4. You will need to do to the 4th power and then deal with that. So it starts to become tedious, but not difficult. Okay, so cosine squared, remember, is 1 plus cosine of 2x over 2. But we need to square that. Okay? So let's see, from here, I'm going to take out a quarter, okay, a 1 over 4, that's the 1/2 that I have squared. And then we have 1 plus cosine of 2x squared. Let me expand this square. So this becomes a quarter times 1 plus 2 cosine of 2x plus cosine squared of 2x. Distributing the 1/4, we get 1/4 plus 1/2 cosine of 2x plus 1/4 cosine squared of 2x. Remember that what we're doing is we are integrating this expression. So far, the first two terms, we already know how to integrate those. Yes? So all we need to do is work with the last one now. So what we do? Well, we have the cosine square. I want to apply this technique one more time. Now, be careful here. When you use the identity, what is this? Who can tell me out loud? What is this? Read it. So read it. What is this? X. Now read this. What does that mean? It means that you need to double whatever you had before. So if I use identity now, what I'm going to have? A 4x. Do you understand this? You need to double the angle. Okay? Whatever you have in here, when you use the identity, you have to double it. So this now becomes 1 over 4 plus 1/2 cosine of 2x plus a quarter times. Now when we use identity, this would be 1 plus cosine of 4x over 2. Do you understand? You need to double them. Okay, did you listen to what I said before?
I didn't understand.
But then ask, because when I say something, there's a reason for that. What is this?
Cos x.
And what is this?
2x.
What happened? It can multiply by 2.
Right.
So x is the argument of the cosine, and when you use identity, it gets doubled. So here now the argument is 2x. When you use identity, it gets doubled.
But not in the body?
This is part of the formula.
Okay.
The thing that gets doubled is the argument. Do you understand this?
Yeah.
Okay. So, and now notice that we basically are done because we know how to integrate this, right? There's no power, and we know how to integrate this thing. So I'm just gonna clean it up now. So this piece right here becomes 1 over 8 plus 1 over 8 cosine of 4x. And so we can combine this 1/4 with this 1 over 8 to give us 3 over 8 plus 1/2 cosine of 2x plus 1 over 8 cosine of 4x. So back in trigonometry or level 47, you will stop here because this was the exercise. Now what do? We go put this in our integral and we integrate. Okay? So this now becomes the integral of 3 over 8 plus 1/2 cosine of 2x plus 1 over 8 cosine of 4x. And as promised, we can do this, right? So that's 3 over 8x plus 1/2 times. So the integral of cosine is sine. So that's sine of 2x over 2 plus 1 over 8 times sine of 4x over 4 plus c. And so we get 3 over 8x plus a quarter sine of 2x plus 1 over 32 sine of 4x. So, moral of the story, it's really just an exercise in 3, okay? So whenever you have a sine or a cosine to an even power, what you have to do is reduce the power until you have no more exponent whatsoever by repeatedly applying the identity, the reduction formula. And then once you have that, you have an expression that you can easily integrate. You put it and you integrate. Okay? That's the technique.
So this is only if it's even, right?
Yes. We already dealt with the odd case. If one of the powers are odd, we know exactly what to do. Separate one guy and make your use of, etc. Notice that the process of solving is completely different, right? It's different. Now, I want you to understand something. Here we just, because the power was 4, we had a constant when we expanded the square, right? Because it's 4, then you have a square here. So when you expand the square, we get a constant, a linear, and quadratic. Okay? Now, what if this power would have been 3? In other words, if this would have been a 6, a cosine to a 6, you have a 3 here, right? So you will need to do a cubic here. Now, how would that look like? It's not going to be as simple as this, right? So you have 4 terms, and then, let me see, it's worth showing that. So imagine that you had, so note, if instead, let's say we had cosine to a 6, then this would be cosine squared cubed. So this is separate from this. So then you will write this as 1 plus cosine of 2x over 2. You cube it. And then you could take out 1 over a. The point is that you're going to get here. This is what I want to talk about. Okay? What do you do in this case? Well, you have to expand it, but let's make sure that what we get is something that we can easily integrate. Because here, the first two are easy to integrate, and this one, the next term that we got, which was a quadratic, then you just use a formula again and you're done. Okay? But here is not so much this case, but we still get something nice. Because the point is that this is now an odd power, okay? So if this would have been an even power, then you will only have even powers in here. And then you know what to do with even powers. But because you have an odd power here, here you're gonna have a mixture of odd and even powers. But the odd cases, we know what to do. We already discussed it, okay? So just keep that in mind. So for example, what would this be? This would be, when you span this cube, this is gonna be the first guy cube plus 3 times the first one squared times the second one plus 3 times the first one cube plus 3 times the first one squared and the second one plus 3 times the second one cube. So the first one times the second one squared, and then plus the last one cube. Okay, that's that. Do you remember binomial coefficients from pre-calculus? For example, let's say that you need to do something to the 5th power. Do you know how to do it quickly without having to multiply?
Yeah, it's 1, 1, 1, 1, 2.
Oh, right.
1,
Do you know how to use that?
more or less.
Okay. I mean, you may not need it, but if you have a high power here, it would be useful to use it. So let me show you. That's called Pascal's triangle.
Yeah.
So this is just FYI, okay? So note binomials. For example, let's say that the problem is this. Let's say that you have a plus b to the n, and you want to span this, okay? How do we do something like this? Okay, you will use the binomial theorem, but instead I'm gonna explain Pascal triangle. I think it's easier to understand, okay? So, but basically, let's see, binomial theorem. This is called the binomial theorem. It tells us this. This is the sum from 0 to n, k equals 0 to n, of the following. And choose k. Okay, this is a combination. These are called the binomial coefficients. I'm going to explain how to get these numbers. Okay, but what's important is what I'm about to write here. There is a pattern when you span, and it's always the following. Here you're going to have a to the k, so a to the n minus k times b to the k. In other words, let's think about what this is for a second. When k is equal to 0, the b is not there, and you have a to the n, to the full power. The next term, which is when k is equal to 1, then the power of a gets reduced by 1, and the power of b gets increased by 1. Okay? So, for example, let's do something a little bit more concrete. If you, let's say that you had a plus b to the 5th, and you wanted to do this. Okay? What this is telling me is that this is going to have something times a to the 5, b to the 0. B to the 0 is 1, so we don't have it. Then plus something, that something is the coefficient, then reduce 1 and increase 1. Then plus something, reduce 1 and increase 1. The total sum always has to be 5. If you add up these two powers, you always get n, right? The total sum is always 5, and what you do is you decrease 1, increase 1. Decrease the first guy, increase the second guy, until you get to b to the 5. So plus something a squared b cubed plus something a b to the 4 plus something and then b to the 5, and the a will be a to the 0. Okay? The question is what goes in the blanks, and this is always the case. Regardless of the power, you will always have this configuration. Okay? So you start with the highest power here, missing the second letter or the second term, whatever this b is, and then the subsequent terms. What you do is decrease the power of the first by 1 and increase the power of the second by 1. You keep on doing that until you get to the last term, which is no first guy, and then you have the second guy to the full power. Okay? Question is what goes in the blanks? Instead of worrying about this, if you like this, I can show you the formula. The formula is n choose k, that's combinations. You compute this by doing n factorial over n minus k factorial times k factorial. and then put the numbers in there, you know, n in this case is 5, and k is going from 0 to 5. This is k equals 0, k equals 1, k equals 2, 3, 4, 5. You can put it here and compute. But instead of remembering this, it's easy to use Pascal triangle. Pascal triangle tells you what these guys are, and it's very easy to build. So let me explain Pascal triangle. So Pascal's triangle for the coefficients. This is to figure out n choose k, okay? And here is what we do. So we begin with a 1, and then we put 1, 1 like this, okay? That's how you begin. Now, every time that we go to the next row, we always begin with a 1 and we finish with a 1, but then in the middle, we're gonna put the sum of the previous two terms of the previous row, but then you will see what happens when there are more than two terms, okay? But for example, the third row is gonna have 3 terms. So first row, 1 term, second row, 2 terms. Here I need 3 numbers, okay? So the first and the last number are always 1. Now, what's the one in the middle? The sum of the previous 2. So this plus this, okay? Now, let's see, the fourth row, how many numbers do I need? 4 numbers. The first one is a 1, the last one is a 1. Now, how do we put the 2 numbers in between? Well, you add the first 2 and you add the other 2. So you start from the beginning and start making pairs and you add them, and that's how you get the number. You understand this? So let's see, tell me what's the next row. 1, 1, so what do I write next?
4,
6, 4. Does that make sense?
Yes.
Do you understand what we just did? Let's do one more. What are the numbers? 5, 10, 10, 5. Do you understand how we are building this triangle?
Yes.
And so on, okay? Now, what's the meaning of these rows? Well, the row has to do with n in the binomial. So this right here is when n is 0. This right here is when n is 1, because think about it. So when n is 0, you have a plus b to the 0. That's 1, right? This is when a plus b is 1. Well, this is just a plus b. So the coefficient of a is 1, the coefficient of b is 1, okay? Now, this third row right here is when n is equal to 2. So that's a plus b squared. Remember, when you span a square, what do you get? A squared plus 2ab plus b squared. Look at the coefficients. 1, 2, 1. Okay? The next one is n equals 3. N equals 3. N equals 4. And n equals 5. So, to do that concrete example that we have here, the numbers that we see in the n equals 5 row, those are the coefficients that go in there. So, this would be a 1. This is a 5. This is a 10. This is a 10. This is a 5. And this is a 1. Okay? For example, when we did the cube here, notice that I put a 3 and a 3. So my numbers were, my coefficients were 1, 3, 3, 1. And those are exactly what you have here for the cube. 1, 3, 3, 1. Okay? So if you're doing a square or cube, maybe you don't really need these. But you know, if you're doing higher powers, you may want to do this instead of distributing all the time. It's gonna be slower to distribute, and you could make mistakes distributing. Okay? So, but if you wanna use this, make sure that you practice it. Practice building the triangle and using it so you get comfortable with it. Okay? This is just in general, whenever you need to do something, a binomial to some power, you can use this idea. Okay? All right. So I guess the point that I wanted to make here is that when the powers are higher in using this technique, first, gets a little bit tedious. Second, you need to understand that, you know, that you need to be dynamic in the way that you use your techniques. The point is that we already know how to deal with this integral. If you have to do this integral in the parentheses, if the question was to compute this integral, we know how to do it because the first term is easy, it's a constant. The second term is just a cosine. We know how to integrate it. This one, the cosine square, how do we integrate this? Reduce formula and done. And this one, what do we do?
Separate cosine.
Very good. The power is odd, so split it, separate the cosine, turn the other piece into sine, use sub, and done. So it's a combination of everything we have discussed. Do you understand this? Okay. All right. Questions on how to deal with even power of just one of them? We still need to talk about what happens when both of them are different than zero. So when the two powers are showing up. But that case is easy, as you're about to see. If you understand this one, then you will understand the next one. Okay, so the remaining case for product sine and cosine, 2.2, is both m and n are different than zero. So m different than zero, n different than zero, and even. Okay, so I'm just gonna do an example to easily illustrate this, but the same thing that I'm gonna do here, it will resemble regardless of the powers. So something like this, the product sine and cosine, both of them are even. It could be 2, 2 or 2, 4 or 4, 4, 4, 6, whatever, doesn't matter. The point is that both of them are even. What's the technique? Well, here's what I'm gonna do. I'm gonna turn one of them into the other one. Because when you have an even power, you can always turn into the other one. Then you distribute. Regardless of when you turn into the other one, it could have terms with even or odd powers, depending on if it's a square or maybe it's a cube or something. But when you distribute this guy, you're just doing +2. So if you have something odd, whatever is left will be odd as well, and you know how to do it. If you have something even, when you distribute, it's always even, and we already know how to deal with even case for one function. Okay? So that's the idea. For example, I don't know, what do you prefer, to turn into cosines or sines? Into sines? Okay. So what I'm gonna do is, I'm gonna take that cosine to the 4, that cosine square, and turn it into a sine square. How? By doing 1 minus sine square. Now we distribute, and what do we get? Sine square minus sine to the 4. So what just happened? We exchanged this integral that we had before for this one. These are two integrals now with even power, but only sine. We know what to do now. Reduce power and all that game that we play above. Okay? It's painful. I mean, this one is easy, but the sine to the 4 is not that pretty, but we can do it. And similarly, if you could have written everything in terms of cosine, and then you would just have powers of cosine here, right? A cosine the other way, cosine to the 4 minus the cosine squared. And we know exactly what to do, okay? So, I mean, I'm not gonna finish this, but now you know exactly what happens here. This becomes two integrals, and now this is, both of these are previous case.
So, Professor, why is it plus? Should it be minus?
Should be minus. Remember, that's to see if you're paying attention.
Well, I am.
I'm not gonna do it because essentially the same thing that we did above, right? And it's gonna take time. Okay, questions. With this, you take care of any integral that multiply the half product of sine and cosine. Questions? Now I'm gonna go to secant and tangent. No, it's more cases. Unfortunately, it's more cases. Because you see, the good thing that we have here is the derivative of sine is cosine, and the other way around also. But with secant and tangent, we don't enjoy those properties. We have the derivative of tangent is secant squared, and the derivative of secant is secant times tangent. So it's a different relationship that we have there. So unfortunately, okay. And we don't have the reduction formulas. We don't have these nice reduction formulas that we have for sine and cosine. You see, even though they look, this is serious. Why do I want to know this? Well, Well, they make our life super easy because we just have a few cases to deal with because we have these nice formulas. For tangent and for secant and tangent, we don't have these reduction formulas. So whenever you have secant to the 4 or secant cube or something like that, you have to do all that kind of stuff, okay? Which we are about to discuss. It's a little bit more complicated, so you will see there are more cases. Okay, any questions on sine and cosine?
Can you go back to the last problem, just like right now?
I know.
Thank you.
Are we good? Something's bothering you. What's bothering you?
Who, me?
Yeah.
Oh, no, I was just gonna laugh because I know you can't respond to this. You know the notes are available online.
Yeah, I thought about it, but I didn't want to repeat.
Just waiting for
No,
it.
the many times that you have said that to me since we've started this class.
Yeah, so why are you gonna ask me?
Because I obviously look at my own notes.
Okay, so I'm gonna switch, but do you understand what I mean by previous case?
Mhm.
So I just don't want to waste the time in redoing the same idea, okay? All right, so in the exam, don't tell me previous case. You have to compute it, right? You have to compute it.
That would be funny though. It would also be a bad video, but it would be funny.
In our defense.
But for
practice
example-
how you play, that's-
For example, look, also try to be, you have to be a little bit smart in the following sense. Here is what I mean. You will see. We did here sine square and we did cosine to the 4. If in the exam they say that I give you this question, sine square, and then you have the other one, you have to compute sine square again. Use it. You can tell me from problem 3, right? You don't have to do the whole computation again. Right? That you can do. But don't tell me, oh, from the class? No. That doesn't work. Right? But you can tell me from problem 3, we have this, and then you put it, and then you use it, right? Also, for example, here, I guess the most tedious one, this was not so tedious. The next one was tedious, right? Cosine to the 4. So I could have reused this, but then instead of going with sines, I would have written this in terms of cosines instead. So I could reuse the cosine to the 4 computation, right? And then just need to do cosine square, which was quick and easy, right? So just keep that in mind. That's what I mean by, be a little bit smart in that sense. If you find that you're gonna redo something that you already did, just quote it. Say, you need to trust that what you did earlier was okay,
Yeah.
right? Otherwise, you're just carrying your mistake over. So keep that in mind as well. All right, so that's sine and cosine. So Franklin is saying something. I don't remember which lesson it is, but when I was experimenting the homework, we do calculations for you. Usually certain problems only have no. Well, for example, the system is smart enough. Like, let's say that the answer is 3, and if you put 2 plus 1, it will take it.
Yeah.
That kind of stuff. Okay,
Right.
and
Yeah.
also something more complicated, it will also reduce it for you behind the scenes, etc.
Yeah.
So that's true.
I know, I take advantage.
But don't, because in the exam you don't.
Hey, it's usually really solvable stuff.
Okay, you can be surprised. All right, so that was both sine and cosines. We're gonna kind of keep the same spirit, okay? And now we secant and tangent. There will be an easy case, actually 2 easy cases for us, and then we'll just be trying to see if any other case is possible. We can reduce it to one of the easy cases whenever possible. Okay. All right. Actually, wait. Unfortunately, I have to give you one more piece of information here. What do? You have a product of sine and cosine and with different angles. For example, you see here in these problems, the angle is always the same. It's xx. And if it would have been 2x, then it would be 2x here.
Oh.
Now, what do you do? You have a 2x here and a 3x here. Yeah, so there are some identities that are called products to sum.
Right.
Now, these are weird. And I honestly would not expect you to know those identities. So I just want you to be aware that they are out there. So in case that you need to do a problem like that, in the homework, you will have to.
But
right?
you would never do
Just
that
look them up and then you can use the identities, okay?
right? That you would never do that to us in the test.
You will see it's super easy, so there's really no point in me testing you on that. But
Oh,
you need to,
perfect.
but you need to be aware of
How to do it.
of the existence and how to do it, okay? So let me explain this. So this is for integrals of the type. So let's say that you want to do sine of something times x times cosine of something times x. And of course, the idea here is that a is different than b, because if a is equal to b, we have the same angle, and then you just use sub. And there are other combinations. It's product sine and cosine. Then it could also be the product of two sines, and it could also be the product of two cosines. And really, you know, it's nothing fancy. It's just that we have some identities that will come to our rescue here, and you need to be aware of them. Once again, this is mentioned in trigonometry. So the identities that we're going to use here is the so-called product to sum formulas. And this is what they say. So if you have the sine of alpha times sine of beta, this is equal to 1/2 times cosine of alpha minus beta minus cosine of alpha plus beta. So this is 1/2 of then cosine of the difference minus cosine of the sum. And that's for product of sine. If you have product of cosine, this is 1/2 cosine of the difference plus cosine of the sum. And if you have a product of a sine and a cosine, it's the same as above, but with sine instead of cosines. So it would be sine of alpha plus beta plus sine of alpha minus beta. Okay, so and as you can see, I mean, the idea is pretty straightforward. There's really not much point, but let me show you number one. Why number one is like that? And we're basically just using those formulas. So for number one, this is the proof. So what's cosine of alpha minus beta? Do you remember this in trigonometry? This is cos plus sine. This is the sum and difference formulas. So this is cosine of alpha, cosine of beta, plus sine of alpha, sine of beta. And then similarly, what's cosine of alpha plus beta? It will be cos minus sine. Okay? Now, why the formulas are like this? The one that we do is we derive the first one using a geometric argument, and then the second one can be easily done by using a trick. Once you know the first one, you can do the second one pretty easily, because you can write plus beta as minus beta, and then use the previous identity. All right. Now, if you are after the product of two sines, here they are. So what do? We just take these two lines and we subtract them. If you subtract the two lines, what do we get? On the left, we get cosine of alpha minus beta minus cosine of alpha plus beta equals, these terms are gone because they are the same, and then you get sine of alpha times sine of beta minus, so as plus, the same thing. So you get twice the quantity. Divide by 2, and then you get the identity. So sine of alpha, sine of beta equals 1/2 times this. Okay? So that's how you get these identities, just playing with the sum and difference formulas of cosine, and for number 3, playing with the sum and difference formulas of sine. Okay? That's how you obtain these identities. And you see, there's really nothing deep happening here, so that's why I'm not going to worry. But you need to be aware of their existence. So I'm just going to do an example. You will use this in a situation like this. Let's say that you want to calculate the integral of cosine of 6x times cosine of 5x. Okay, let's say that you want to do this integral. The angles are different, so the previous techniques do not work. But here we see a product of cosine, so which item should we use, 1, 2, or 3? So we use identity number 2, and that says it's 1/2 cosine of the difference plus cosine of the sum. So this would be by number 2, that's going to be 1/2 times cosine of 6 minus 5 plus cosine of 6 plus 5. Right? Cosine of the difference plus cosine of the sum, and now that's easy. So integral of cosine, that's sine, and this will be sine of 11x over 11. You understand this? So I don't think I need to say anything more about this. Any of the 3 combinations that you saw above, if it pops up, then just use the corresponding identity. Okay, that's all. Yes.
Will we ever get a problem? Oh, I guess we could. But will we realistically get a problem where one of those will be put to a power like cosine, a third 6x times cosine 5x?
That would be hard then.
That's what I'm saying.
That's a
I
good
need to
question.
know.
Not in this course.
Yeah, that's gonna be hard.
Does that come free?
If you get that, okay, if you get that, here is what I would do. If you get that, first, you can always match the powers by taking out whatever is extra from one of the 2 powers. And the reason why I'm doing that is so that then you can put the product to that same power together, and group them together. Then you have a product, you can use the formula to write as a sum. You have to distribute that power. But then we have them independently, so we know how to deal with those powers. We've already discussed that. Now, the problem is that you have something else that you need to distribute. Right? Then you will need to distribute that term. And because the angles are different, you have to repeat the same process for each of the terms that you obtain. But the total degree is less, so at some point this process is going to stop. I don't want to waste too much time on that, but let me just do, for example, imagine that you had cosine squared of x times sine of 3x. Let's make it simple, something like this. Okay, how do we do this? Well, what I'm saying is, okay, I want the powers to be the same, so I'm gonna take out one cosine, just leave it here, and then the other 2, I'm gonna put them together. In this case, because the power is 1, then it's like that. But if this would have been a square and this one a cube, they have a cosine, and then you will have a square here. Understand? Okay. So why am I doing this? Because now I'm gonna use the identity to split this, to write it as a sum. So let's see, that's product of sine and cosine. That is number 3. So that's 1/2 the sine of the sum plus the sine of the difference. So 1/2, I'm gonna put it outside. The sine of the sum, the sine of 4x, plus the sine of the difference. Okay, now this is important. Here the sine came first, so the angle that comes first is the one for the sine, and the one for the cosine. Okay, alpha is the angle of the sine, so it will be 3x minus x, because 3x is the angle of the sine. Okay. All right. Now we need to distribute the cosine. And I separated already as 2 integrals. And the 1/2 is multiplying the whole thing. But now the point is that now we have another product of sine and cosine, so we use the identity again. And here another product of sine and cosine, we use the identity again. Right? And once we use the identity, then that's it. Everything becomes no products, and then you can finish the integral. So, but then again, if the powers are higher, then this is more cumbersome because it's not as easy as this one. You have to see the power, and then, but the idea is that the powers that you are going to obtain are going to be less than what you had before, so you can always do something about it. So now, use identity. Again. for both of these. Okay? But John, I don't think you're gonna get something like that, let's say in the homework, and definitely not in the exam. There's no point in this.
I would say probably.
But you know, it can be done. I don't want to, because I don't want to say no, it cannot be done.
Can be done, but it won't be done.
Okay. Are we okay with this? All right. Again, don't put too much stress on this. If you get a question like this on the homework, just go to the notes, look at the identities, and then you know how to get it done quick. Okay. So, having said that, today I do need to leave 10 minutes early. So we have 10 minutes. So let me, I guess, show you the easy case for secant and tangent, and then do it next week. All right, so product of secant and tangent. So again, the idea here is goal is to deal with secant to some power times tangent to some power. Okay. Helpful identities to remember from here is a relationship between secant and tangent, which is the 1 plus tangent squared equals secant squared. So this is a way of turning secants into tangents, right? And equivalently from here it follows that therefore tangent squared can be written as secant squared minus 1, right? So this is a way of going from tangent to secant. So you can go back and forth, just like we can between sine and cosine, you can between tangent and secant, okay? As long as the power is even, that's what this is telling us. It's also important to remember the derivatives, because remember, each derivative formula gives you an integral formula. So what's the derivative of tangent? Secant squared. And what's the derivative of secant? Secant tangent. Okay? So if you need to integrate secant squared, what's the answer? Tangent. If you need to integrate secant times tangent, that's it, right? All right. Something that will also be helpful is to know what's the integral of secant. We discussed this last week. Anybody remember? I told you to remember the formula. That's ln of absolute value of secant plus tangent. Okay? Something helpful also is to understand how to find the integral of tangent. What's the integral of tangent? How do we do this? How do we do integral of tangent? When you are out of ideas, here is an advice. If you are out of ideas, turn it into sines and cosines, and then see if you can make it work from there. Okay? So technically, all of these things that we're going to discuss with secants and tangents, you can turn it into sine and cosine. Just that there will be fractions, and then sometimes it's not that straightforward because the process we discussed, they were not fractions. Okay? So,
Can you say that?
but here, this is easy because here we can let u be cosine, right? And then du will be negative sine. So this becomes the integral of 1 over u minus du. So it will be negative ln absolute value of u. So that's negative ln absolute value of cosine. But typically, instead of using this, what we do is we bring the negative 1 to the top, and that's 1 over cosine, which becomes secant. So we like to write this as ln of absolute value of secant. That's how I'm going to be writing this. Okay? What I did was I took the negative and I put it here as a power. Okay? And cosine to negative 1 is 1 over cosine, which is secant. So you should remember this. Integral of secant is ln of secant plus tangent. That you need to know. And integral of tangent is ln of absolute value of secant. If you want, you don't really need to memorize this because it's easy enough that you can get it on your own. The idea is write a sine over cosine, and then you solve. Okay? All right. So these are the formulas. Now, let me at least show you the easy case. Two easy cases. The first one is when m is 2. So remember here, m is the power of secant. If you have a secant square, it's super easy. Why? Because you can let u equals tangent, and then du is secant square, right? So it's a super easy case. So for example, so in general, I'm just going to do it in general. If you have the integral of secant square times whatever tangent you want, doesn't matter the power, just let u be equals to tangent, because then du is secant square. So this is the integral of u to the n du, that's u to the n plus 1. So that's just tangent to the n plus 1 of x, or n plus 1. Okay? That's what you do when the power of secant is 2. And then the other easy case is when the power of tangent is 1. So if n is equal to 1, so that means that you have secant to whatever power you want, but then only one tangent. If there is no secant whatsoever, we know what to do, right? We know what's the integral of tangent. So what if you have tangent times some power of secant, whatever it is? That's what I'm about to discuss now. So let's say m is different than 0, because if m is 0, we know already what to do. It's just tangent. Well, we do something similar that we have done before, because we have some secant, we separate secant, and then we're going to separate a secant with the tangent, so a secant tangent. We let u equals secant, and now du is secant tangent, right? So if you only have one tangent and then a bunch of secants, this is what you do. Separate one secant together with the tangent, and that will be our du. We're going to let u equal secant, then derivative of secant is secant tangent. So this becomes the integral of u to the m minus 1 du. So that's just u to the m over m. So we get secant to the m over m. Do you understand these two cases? All right, good. So those are the easy ones. Now, let's see. From the other cases, and I want to take attendance, so I'm gonna let you work on something as I take attendance. The first one that we're gonna do is when the power of secant is even, tangent is whatever you want. So m even, but different than 0. When m is 0, it's a different story. But if the power of secant is even, and then different than 0, and n is anything, then how do we do this? For example, I'm going to show you one, and then I'm going to ask you to do another one. And just to show you that it doesn't matter what it is, I'm going to put here tangent to the 30. To the 30th power. Doesn't matter what it is. I didn't put secant square, because if I put secant square, that's a super easy case, right? You just let u equals tangent, and then. So what you do if you have a 4? So this is the case that we're analyzing when the power is even for secant, and tangent is whatever you want. So what's the strategy? Separate secant square, because you separate secant square, what remains is an even power, because even minus 2 is still even, yes? That even power of secant turn it into tangent using the identity, and then make u sum. U equals tangent, the u is the secant square that you separate. Okay? That's the plan. So what do we do? So I'm gonna separate secant square. I'm gonna put it here next to my dx. And then this secant square, I'm gonna turn it into tangent. How do we turn it into tangent? Secant square is tangent square plus 1, right? So that's 1 plus tangent square. And so now we make a u sum, because we now have this integral 1 plus tangent square times tangent to the 30 times secant squared dx. We let u equals tangent du secant squared. So this now becomes the integral of 1 plus u squared times u to the 30 du. It doesn't really matter what power we have for tangent because it doesn't even add complexity. We just need to distribute this guy. So we don't even need to do anything to the 30th power, really, a binomial or nothing like that. What adds complexity to the problem is this guy, the 4. If that's higher, then we may need to expand something here, okay? And that's what makes it a little bit painful. So then this becomes u to the 30 plus u to the 32. So that's u to the 31 over 31 plus u to the 33 over 33. So we get 1 over 31 tangent to the 31 plus 1 over 33 tangent to the 32. Did you understand? Try this one. And then I take attendance and we call it. No, I can't. I have to go. I was gonna give you. Okay, we are few, so we can take attendance quickly. Try this and see if you can do it. Quickly, what's the technique? What do we need to do?
You split the secant into 3 sections.
So secant square here, right? Then what do we do with the secant to the 4?
You split that time.
We write it as secant square, right? And then the tangent stays there. And then what do we do with the secant square? So 1 plus tangent squared, right? And now u sub time. U equals tangent, and then this is our du, right? So u equals tangent, and this guy right here is a du. And then you do a polynomial. Is that okay? All right, so on Tuesday, we're gonna finish we have a bunch of other cases. If you want to start thinking about how to do the other cases, I mean, the videos also explain this, so try to make sense of the videos, etc. Then on Tuesday, we put it all together.